This presentation is a training on the AE-150 partial discharge positioning system on power transformer. So quick words about NDB. Our core business is to manufacture test equipment for utility and for all energized accessories within a grid. What we do can be divided in 5 main groups. And today we're going to talk about the substation test equipment, which the AE-150 is part. So we also do turn ratio tester. We do winding resistance tester, CT tester in that group. We also do partial discharge test equipment for switchgear, cables, elbow, overhead accessories. So the AE-150 is a mix in between. We also do cable identify and phase identify items. We do also transformer distribution tester for safety, and we have a complete line of micro ohm meters. Our manufacture, the R&D and the manufacture and the production is located in the eastern part of Canada, in the city of Quebec. But we also have 2 sales offices. One sales office is located in Mexico City, and the other one is in Germany, covering Europe. But all manufacturers, after sales, production, and R&D are based in Quebec. The 2 other offices are sales office only. So unit overview. Sometimes the goal or the unit goal is misunderstood. So the AE-150 will provide a location, will provide a localization, will provide an area of where the partial discharge is located. It's a tool to help to take better decision on your transformer. But what's misunderstood, it's not a PD measurement device. This can confirm that you have a PD inside your transformer, but this tool is not a PD measurement device. It won't tell you how bad is your discharge inside your transformer. This tool will tell you where it is. And this is what gets confused sometimes. So where do we use the AE-150? And this is where you're going to understand where we're using it. So we're not using the AE-150 before any other tool. So we use it after that we have a suspicious transformer. And this is important because DGA, this is an example DGA, but DGA is easy to do, is cheap, and easy to obtain. So that's an example, but you can, if you're a manufacturer, you can do conductive test in your lab. So it leads you to a suspicious transformer, and then you will use the AE-150. So it's like having another tool after that you have a suspicious transformer. So it comes after your current tool. So the unit can be used into monitoring. So the unit can be left on the transformer. You see monitoring over here. So it can be left on site on the transformer, magnetized for a certain period of time. So let's say a week, because PD may not be ignite every time, so at each minute. So PD is depending on the voltage, depending on humidities, depending on many aspects of your grid. So prior to do your inspection, it's good to leave the unit on the transformer for monitoring, and then you can do your inspection at the right time. So it may be at night, in the morning, during the weekend when the load is lower, but at least you know when the activities increase or when the PDs ignite. And then you get a location. And based on this location, you can look to the mechanical drawing, pre-order parts, wait for them, contact the manufacturer, transfer the load to another transformer. Any kind of tool that you have is good to take a better decision and plan your action. So instead of working blindly, you're now in full control of your work, and you can, let's say, either repair on site or even just order a new one because the parts are too expensive, but at least you have the reason why, you have the answer. This is the unit operation flowchart, and we will go into all those points one by one in this training. So we will continuously come back to this chart in order to explain you where are we in this process. So first, the first things to do in the AE-150 is to set up the unit on the transformer. Well, the unit is magnetized. Okay, you see you have strong magnets on the transformer, and the unit is magnetized on the transformer steel wall. And one channel, the electric channel, this one here, is connected to an HFCT or as an accessories to a UHF antenna inside the transformer. But this example there is the same. The electric channel is connected to either an antenna or an HFCTs on the ground strap. Then you need to synchronize the unit. So you have a wireless phasing transmitter that is connected to an outlet, a standard outlet, to 50 or 60 hertz depending on where you are, and it goes from 120 to 240 volts. So the unit, when connected, the phasing transmitter will automatically transmit the phase to the unit. So the unit becomes synchronized to the network phase, and it's wireless. And then you need to be connected. I mean, your computer yourself to be connected to the unit, either to transmit commands or receive the data. So we have either a cable, so a cable that runs in between your PC and the AE-150, or we have a wireless optional transmitter module. So if you're using the wireless, you are totally isolated from the unit, from the transformer for safety, but it's one or the other that will transmit command and receive the data. So before sticking or placing the AE-150 on the transformer, it's very, very important to add the acoustic coupling on each sensor. And don't forget, after a position, you must reapply the acoustic coupling. Each position you need acoustic coupling, and this coupling will, in fact, it will replace the air gap in between your acoustic sensor and the transformer wall. So this thing will remove the air that act like a isolation, let's say, material between your sensor and the transformer wall. So it's very, very important to add the acoustic coupling on each position. And then make sure that your sensor are totally in contact with the structure. So you see sometimes there is an angle, so make sure to push all 4 sensors around to make sure that you have good contact with the steel structure. Then to release or to place the unit on the transformer wall, we have release, magnet release, that will help you to position the unit on the transformer. So just be careful about those magnets, they are quite strong. So the electric channel is located under the unit. It's a standard BNC cable that runs between the AE-150 and the HFCT or the UHF antenna. But it's only a standard BNC which is provided in the case. Those are examples of installation. On the left over here, we can see that the HFCT is just located on the ground. There is no direction, so it can be installed one way or the other. It's on the transformer ground, and later we'll see some aspect of it. And on the right, you see it's the same thing, but it's a solid bar. And something important here, we have an optional 20 millimeters inside opening, and for majority of the transformer we do recommend to use the 60 millimeters opening clamp. This is what you are seeing on the picture. The black one is the 60 millimeters. Communication option, I spoke briefly about it. We have two options. No, not two options. We have one option and one cable that comes with the unit. So the one that comes is the wired communication. It's a cable that runs between the AE-150 and your computer. So on one side is USB and the other side is the dedicated round connector. So this cable comes with the unit. It's not an accessories. And if you are looking for better transfer speed, that's the option that you should use. But if you want to be isolated for any reason, and sometimes some utility they don't recommend, you need to be isolated from the transformer for safety, you can use the wireless module, and this module is connected again with USB to your computer and will communicate with the AE-150. The distance or the range between your, let's say, this module and the AE-150 can be up to 100 meters. And when I say up to, it doesn't mean that it cannot go over, but it can also be lower than 100 depending on the environment. So if you are into factories that generate lots of magnetic emission noise, this distance may be lower. So it could be 20 or 10. But I don't know upfront. Something sure, we do test them to be workable up to 100 meters in the factories. When choosing your option, the way to toggle the communication mode on the unit, on the AE-150, is the front button on the front membrane. So you will have to press this button here, a long press of 4 seconds, and then the LED over here. There is a little image. It's an antenna. So the LED beside the antenna will disappear, meaning that you're wired. And if the LED is lit, you're wireless. So it's kind of intuitive, but this is something that you should remember. So it's very easy. The unit only have on-off button and communication toggle mode on the unit. All the rest is controlled by the Miradar software. So once that you have set up the unit on the transformer, it's time to set up the software, the Miradar software. So prior to use the software, it must be installed on your computer, and something very important, make sure to accept the FTDI serial driver on your computer. So this is mandatory. Accept them, they will be installed in your computer, and you will be able to communicate with the unit. Without the FTDI driver, you cannot communicate with the unit. On my next slide, I will open the Miradar software and we will go through some tab on the control panel. So we'll go through the transformer definition, the communication setting, the AE-150, location, and the gain setting, the automatic gain setting. So this is an overview of Miradar software. At the beginning, you'll see on the left, you have the control panel and you have the data analysis panel. So all the data will be stored over here and that will be covered later. But at the beginning, all the control of the unit will be done by the control panel. So before starting a new inspection, we will have to fill those tabs. So the transformer size, the communication setting, the position of the unit on the transformer tank, and then finally control the unit remotely. So the first one, the transformer tab, will hold the serial number, which can be anything, letters and numbers. This serial number will be exported in your report after your job. So first thing, you will have to define the transformer dimension. So maybe you have the drawings, maybe you'll need to measure it, or maybe you also need to approximate it. But as more precise the dimension is, the more precision you will obtain on your position. So you can move the current tank dimension. You can, with the control button, you can zoom in or zoom out. You see the tank origin, so that's 0, 0, 0. So it's defined like in mathematics X, Y, and Z. So right now the tank is defined in centimeters, but it could be whatever. Let's make it 100 by 100 by 100 to make it smaller. So it will automatically adjust the shape of the tank. So you also have a reminder. So you have the width, height, and depth. What are the axis of it? And optional information over here. Sorry, open in my second screen. It's an optional tab. It's not mandatory, but it contains optional field that could be helpful, could be needed, but again, it's not mandatory. The only thing it is the serial number, so you can accept. So now you have defined the transformer. The second thing is to set up the communication with the AE-150. Right now, I don't have any unit connected to my computer, so either wire or wireless, I cannot establish a communication. But there's two ways, and those two methods of communication will be defined later in this presentation. So let's say if you're wired or wireless, any of them, you will need to select a COM port attached to it. So either you're wired, so the unit will be seen as a communication port, and same thing if it's wireless. The unit, or let's say the communication link, is seen as a communication port. So you refresh, select it, and connect on it. So the status will turn online. the top status over here will be switched to online. The serial number of the unit will appear over here, and if you are wireless, you will see the signal strength of the communication link appear over here. And this is a good indication that you can either move away to get under shade, to get on the building, or even get closer. It depends on your environment. Something important is if you are losing the communication, let's say that you accidentally detach the communication link, either wire or wireless, make sure to disconnect the link before making another detection. So those two will work together. So as your link is established, you will see that you're online, and this little LED, if I could call it an LED, is a heartbeat. So as each second, the unit will toggle the heartbeat, and this will tell you that you're connected online. You will also have the battery indicator, the battery level of the AE-150, and when connected, the phase sync module will also transmit the phase to the unit, and the unit will return the frequencies of that phase. So in North America, that'll be 60 hertz, and the rest of the world, that'll be 50. And if you are a manufacturer, that'll be something else, like 400 hertz. So that's the communication panel. And then your first position must also be defined. Let's say the first and all position around the transformer must be defined in the software. So the first position, you choose it to be as well, let's say easy for you. Don't choose it under fence, so you choose it on the flat surface, on the phase that fits your, let's say, fits your thoughts. Right now, it's defined on the front, so you see the 4 sensor on the unit. Okay, the little star over here is sensor number 1. So that's sensor number 1, 2, 3, and 4, and they are reflected over here as sensor number 1, 2, 3, and 4. So right now, the first position is defined on the front, but it could be on the right, back, top, bottom, or left, side wall. The unit is now standard. There's no rotation, but if for any reason you have a mechanical obstacle on your way, you can rotate it, let's say clockwise 90 degrees. So your sensor number 1 is now bottom right, which is this one over here. So the software must know where is your unit. So, but let's make it standard on the front, and the center of the unit must be measured on each position. And the center of the unit is the little cross over here, so that location must be measured against the origin of the tank. So right now it's 50, 50, and the z-axis is 0 because we're on the front. So that's the z-axis. So the depth. So you can move it. If I move it to 66, so the unit is moving right, and if I add distance from the y, so we go up, and so on, and it's all on the front. So those measurements must be accurate, again, to obtain accurate position inside the tank. This section here is if you are working with small transformer that have a lot of mechanical obstacle around it, and sensor must be detached. It could be an option. So you will use the older the accessories holder to hold separately the sensor on its own. So the unit will be detached and each sensor will be defined separately. So make sure to enter the right one. So sense the sensor 1, 2, and 3 versus the center of the unit at that point. So they're all gonna have to be measured separately. So it's 4 times 3 measurements. So it makes 12 measurements. So you have more way to make a mistake. So that's why measuring only one time the center of the unit, it's much easier than taking 12 measurements. So as the first AE-150 location is key in, you can proceed with the control. The control is the tab where you control the unit remotely with your computer, and this tab will be covered in the next slide. One point that was not covered in my previous video was the auto setting gain. So this can be achieved by the button over here, the auto setting gain. And this is very, very important. So on each position number 1 all the way to the last one, you must set the gain, and the gain are set automatically. So this is a nice feature because it's automatic, so you don't need to care about the gain setting, but you must do it on all positions. And the goal of setting the gain for each channel, each acoustic channel, is to be able to capture acoustic. So you need to crank up the gain level, but you don't want to have too much gain because you don't want to saturate the channel. So it's a mix in between. So it's automatic. So the unit, as you press auto setting, will crank the gain in order to hear acoustic, but not all the way to saturate it. So it's just set the gain to a limit where you don't get saturation and you have enough gain to listen to the acoustic. And this is mandatory. On each position, you need gel, okay, the acoustic gel, and you need to set the gain. So each time you come to a new position, you need to key in the location XYZ, transformer, wall, side, and to reset the gain. Always, every position. So after your software setup, the first thing that you do on site, and I repeat it, the first thing to do on site is to take PRPDs. I will explain you what is a PRPD, but the PRPD is a tool for you to analyze the activity. So the question to ask yourself, from my actual position, let's say from my first position, am I detecting suspicious activities on this transformer? So that's the question that we should ask ourselves. So let's go through. So I will talk about PRPD definition, example, multiple pattern, and how to set the trigger. Definition now. So PRPDs is a graphical representation of the activities on a cycle. So I'm saying on a cycle, on a network cycle. And it's representing the activities over time. So let's have a look. The y-axis, okay? The y-axis on the graph is the amplitude. So the amplitude over here is in volts. So it goes from microvolts to volts. So that's an easy one. The x-axis, okay, represent the phase angle. So the phase angle of a cycle. So it goes from 0 to 360 degrees. But the z-axis is represented by the color. So as the color gets warmer or hotter, it becomes red. It means that the activities over cycle is repeating. So on the example over here, we can see that this spot of activity and this spot over here repeats over time because of the color, the red color that gets hotter on those spots. So compared to this blue little spot, it only appears once, but as you get this amplitude to exactly 150 degrees over time, so as you get repetitive sampling at this specific angle and amplitude, the color's changing. So as the colors change, it means that the activity repeats over time. So it's normal that we take lots of sample to get that kind of graph. So to obtain a graph like this, we may take hundreds of cycles. So we need multiple sampling of a cycle to build that graph. So it takes time, but this is a representation of the activities over time. So that's like a picture of what's happening. This is an example, multiple example of PRPD, of the electric channel PRPDs. So you see the one on the left, on the top left, this one here. This one is totally flat, so there is no activities over a cycle at all. So it's always flat. So it means that we're looking to noise because we will get something, but there is no phase relation over time at this position. So the conclusion from that first one is I need to move to another location looking for activities. But all the others are very suspect. So we can notice activity that repeats 2 times per cycle. Okay, this is the majority of the time. So it does repeat on the positive and the alternate and the negative alternate. So 2 times per cycle. So this is quite normal. But what we are looking for, repetitive pattern over time, over cycle and over time. So it must be repetitive. So this is what we're looking for. Those are example, but of acoustic. They are a little bit different because acoustic and electric behavior is not the same. So in the transformer, so one is traveling in oil and steel, and the other one is conducted pulses that runs to ground. So it's not the same phenomena, but the same concept apply. The first one here is nothing. It's totally noise. There is nothing. The amplitude over here, drawing the amplitude is low. It's flat over a cycle over here. So there's nothing to do. So the conclusion would be there's nothing. Let's have a move. Let's move either left, right, or change side. But all the others are suspicious enough to continue the investigation. So same concept apply to bumpy, shapy waves over cycle, and the waves or the types of the shape will depend on the nature of the PD, but we won't get into it. So this is what we're looking for. Suspicious PRPDs. This is what we're looking for. This is option of the PRPD. We can set the resolution, but this is not something that I do recommend. PRPD can be set all the way from 256 by 256. So it means the granularity, the definition of the PRPD can be changed. So 128 by 128 is a good trade-off, because as you can see, 64 by 64, it's good, but it doesn't take that much longer to transfer the data, because it takes longer, well, not longer, it takes the same time to acquire the PRPD. It's just the transfer time that it's longer. So it takes anyway, you see, we're acquiring thousands of cycles, and at 50 hertz, it means it's 20 seconds. So we're acquiring, the acquire time is 20 seconds, and the transfer time depends on the resolution. So it may take 1, 2, or 3 seconds plus the 20. So the doesn't make a very big difference. So I do recommend that you set it to 128 by 128, which is the default resolution for PRPD. That's the only option that you can do. Something that you must consider is the multiple problems can be found in your transformer. So you may have more than one PD in your transformer. They can be spread on different side or on the same side but different location, and they will produce different pattern if you're in your PRPDs. So like in this example, this could be generated by one PD location. This one can be also another one, and this one can also be a third one. So we will need to focus on each of them separately. Focusing on each of them may or may not, but it may leads to 3 different PD locations. So we will treat them as separate in the same file, but we will treat them as 3 separate events, and we will focus on each of them. Maybe we will get more than one PD position, but between you and me, I've made lots of inspection on many transformer, and I've never seen more than one PD location. Doesn't mean that it does not exist. The system was designed for, but I've never seen it. So I'm just telling you that it's possible. So how do we do it? How will we treat more than one PD location? We will do it by the use of cursor. So we will use cursor as starting, stop, so start and amplitude. So we will work like in this example, we have the start cursor, the stop cursor, and the amplitude cursor. So in this example, we will only focus on activity that is in between the start, the stop, and the amplitude. So this is where we are going to focus only. So all the rest will disappear. We will only focus on one specific event. So the cursor are manually positioned. So it's up to you. It can be a little bit farther or left, but the goal is to identify just one thing. Okay, so if it would have been placed over here, start, stop, and amplitude would also be good, because we would have covered just this area here. So the goal is to just isolate one part and just focus on that part. Forget all the rest. So once that you have isolated an event, and that event should be or must be the one that have the most or the highest amplitude. Just before going into this slide, we can see that both event PRPD, suspicious event, look similar. They have the same shape. The shapes look similar. But the one on the right, this one here, seems to be more repetitive over time because the color is have more red color on it. Because the color is more hot, it means that it have it more sustain over time. So it does repeat a little bit more over time. So I choose to trig on this one here instead of this one. This one here doesn't have red. The one on the right looks more repetitive, to my opinion, and this is what you need to develop. Okay, which one seems to be more active? So this one for me. So what I did isolate just this little portion over here with the start stop. So it means it's from start angle to stop angle to this specific amplitude. To be honest, I cannot read it from my LCD screen. But as you move it, the angle will move. As you move the stop cursor, the angle will move, and as you move the amplitude, this one here, the amplitude will also move. So you move left, right, and the amplitude to isolate just the portion. Well, in fact, the portion is it's like a window that you're scrolling. And for sure, you are also selecting what channel. Are they acoustic, channel 4, 3, 2, and 1, or electric? This one is the electric, is the HFCT or the antenna. So once you click the set the trigger, it will copy the selection, the electric channel, all the way to the trigger channel. And it will transfer start and stop angle into the control panel. So and the amplitude. Okay, so I'm taking one step. The goal is from the position that we are looking to suspicious activity. If we have a suspicious activity, we must focus on it to do the second part, which is waveform, and waveform will give us the location. But right now, the only question that we are asking ourselves, am I having activity? Am I having suspicious activity from this position? And I want to focus on it to access the second part. Okay, so first question, yes, I do have suspicious activity on my electric channel. Then I'm focusing on the activity that is the more suspicious, and then I transfer the angle and the amplitude to the control panel in order to go to the second step, which is waveforms. Just one point, because before going to the second one, this is a real example. This is a real case. I made it myself. You can see on the picture that the ground strap is distributed over the transformer. See the picture on the bottom here. We have a ground that goes to a connection bar and another ground that goes to a second connection bar, and that connection goes to ground. Okay, it's not unusual to have more ground connection on the transformer, and it may have more than that, but that's a real example. So I was taking measurement number 1 to this section of the ground, and you see little bumpy things over here and over here. So is it the worst, or is it the highest amplitude that I can get? That was my question. The answer was unknown at that point. So I moved my HFCT to position number 2, so which is left side. And then I can still see the little bumpy things. Okay, same thing with more noise. So this ground is a better ground for high frequency. So it's less impedant to high frequency. So there is more energy that flow from that path than the other one. But is it the best section that I can get? So number 3 was try and see that's much better place to take my high frequency measurement. So what you need to remember if you are on a transformer with multiple ground points, I would say you may need to take or to try all ground access point and to take a PRPD and then choose the one that is showing the more energy. In this example, that was number 3, and the inspection remained with the HFCT on position number 3 only because I knew it was less impedant and a better place to take my measurement. Okay, so this one now, waveforms. So the unit was set on the transformer. I have entered the position. I have set up the gain. Okay, auto set the gain. I made a PRPDs, and my question was, do I have suspect PRPDs? And the answer was yes. So I set the trigger, the cursor and the amplitude to my suspicious activity spot, and then I want to do waveform, and waveform will be needed to obtain points and vector of a possible location. So we'll talk about basic operation, technical data, the acoustic path, and how to remove the noise. All those points will be covered in this section. So the basic concept behind the AE-150 and how to detect the location is based on time of arrival. Okay, so that point here, the AE-150 is an accurate time measuring device. The position of the PD is based on timing. As told in my first slide, this is not a measuring device or PD measuring device, it's a timing positioning device, if I could say. Okay, let's make a 2-dimension example. Okay, this point here is PD. Okay, this point is a PD location. That point is PD. So there is an arc, electric arc, that is generated from a point to another point, and that arc will generate acoustic emission. They are pressure waves that are flowing in the oil, and as they flow, it takes time to reach point. So the first sensor to be hit by the pressure wave is sensor number 4, and then it's number 1 as it continues to flow into the oil and steel, and then sensor number 3 gets hit, and the last one that gets hit is number 2. So sensor number 2. So based on the time difference that sensor are hit, we will deduct a location, a position of where the source is. And in this two-dimensional example, the only possible location is over there, based on timing. So that's all. That's the key. Timing is the key. We're not measuring magnitude, we are measuring time difference. This is some technical data. This time we made a view on, let's say, oil. This is oil inside a transformer, and this is a transformer wall. Okay, so and this is the PD source. As told, this source is generating an arc, and that arc is producing acoustic that travel into oil and steel. So as the wave, or as the acoustic pressure wave is traveling in oil, it runs all the way to the sensor here, the detector over here. This is one acoustic sensor of the AE-150. But this path here is only traveling in oil. So it's oil only, and it's traveling at 1.4 kilometers per second. So it takes a second to travel 1 kilometer. That makes no sense for a transformer, but you get the concept. But as we know, that speed of sound in steel is about 4 times quicker. We have another path. So the path is we're traveling less time at low speed in oil, and then we're traveling faster in the steel. So we may have 2 different paths or traveling path for acoustic. One will be traveling in oil, and the other one will be traveling in oil and steel. So we call it combined path. So the direct path is only traveling in oil. So it's oil only, low speed, but as the sensor will be hit and no reflection would have occurred in between, we will get lots of energy. Okay, the energy will be much higher than the combined path. So the combined path over here will have less energy, but it will be the fastest because we're traveling less time in oil and we're traveling in steel. So the combined path, I would say, could be. It doesn't mean that it does exist. It depends on the location. But it will be traveling in oil and steel faster, but the resulting energy captured by the sensor will be less, because you see in this example over here, I will have reflection. So I'm losing energy over here, and I'm also losing energy as I'm traveling into the steel. But don't worry, they do exist, the direct and the combined path, and the software will handle it for you. What are we looking for now? Now we know that we have combined and direct path. Both of them will exist, but we are looking for what we call, and what you will see in the software, we are looking for time of arrival, the TOA, time of arrival. The time of arrival is the first moment where the acoustic sensor are capturing acoustic energy or electric. Let's say it again. We are looking at the moment where sensors are capturing the energy, whatever it's conducted pulse or it's pressure wave, acoustic pressure waves. So in this example, we can see that we have direct path that comes later after the combined path. The combined path is coming first with lower energy, and then we see the direct path. And what we are looking for is that point here. And that point is the junction between the nothing, let's say nothing and spark. And when I say nothing, this is an important word because there won't be nothing in the transformer. The transformer is energized, and this is our challenge. The challenge is to remove the noise in order to see the time of arrival, because we're looking to very, very small amount of energy within an energized transformer that is vibrating, that have pumps and fans, winds, vibrations, and lots of things on the field that will or can cover the time of arrival that we are looking for. And this is the key. Without noise reduction algorithm, we are totally blind. We're not able to work. So we need to remove the noise to identify the exact time of arrival. So what we do, or how do we do it? We use a technique that is called the averaging. And the averaging techniques is based on the fact that the noise is random. So it is random over time. So sometimes the noise gets positive, sometimes it gets negative, sometimes the amplitude is high, something it's lower. But if you make many measurements, if you are acquiring lots of sample over time, you add them together and you divide by the numbers of sample that you are acquiring, the random noise will get down to zero because it's random. But what we're looking for is always the same thing, same place, same shape over time. It's PD because the PD is not moving. We are in one position, the PD stays at the same position. So we get the same thing over and over and over, but the noise gets totally random, but we are capturing the same thing over cycle. So the random disappear and what's remain at same plane, same shape, at same time will stay. So this is an example of before we see that we have something, we see that we have thing that repeats over time, but when the noise is removed, we see straight lines, let's say silence, and then we see activity that's coming after a silence. And this is the key to identify the time of arrival. This is an example, but this is a real example of 16. If we take 16 measurements, we add them together and we divide it by 16. So we take 16, let's say 16 acquisition, 16 different cycle, and we divide by 16. This is what we get. But if we take more, 32, we are the noise get lower. What we're looking for remain the same, and this is 64. This is an example of 64. It doesn't mean that 64 will be enough in your transformer, in your location. It doesn't mean. This example, it was enough. And if it's enough, don't push it farther because you don't want to disturb the waveform, the remaining waveform. But right now, we can see that 64 was good enough to remove the noise, and that will be good to identify the time of arrival. And then what we can do is to zoom in. This is the same thing, but I had zoom in into the waveform, and I can clearly identify the time of arrival. So that point, this point here, it's very, very clear. It's totally flat, and then I get the acoustic pressure waves. Some setting in the waveform panel. Again, it's into the control. Remember that we have set those tab before, okay, and all those things are or can be found in the control tab of Miradar. So this is the averaging. We can set from one sampling, which means no averaging, all the way to 2048. So this is the maximum. And what I do recommend is to start between 64 and 256. So this section here is a good trade-off between you don't have to wait long and you can see things. So you can start to 128 and see if it's good enough. And if it's not enough, crank it up. Don't start at 2048 because you may wait too long and anyway for nothing, because you may realize at the end that this was not something that you were looking for. So suggestion is to start at 256. Another aspect when starting an acquisition, a waveform acquisition, is to set the buffer size and the trigger channel. So we've decided to trig on a specific channel by placing the cursor around a suspicious event. So the trigger channel must be identified. So when you select and transfer it, this one will be placed automatically, but you can do it manually. So you can use the little arrow over here to select to trig on acoustic channel 1, 2, and 3, or the electric channel. And then what you need to select is the buffer length. And this is important because if you don't know what you're doing, you can pass over what you're looking for. And let me explain. If your trigger channel is the electric, it means that on a time base, you will see first the electric channel, and after that, you'll see the acoustic coming. So the first thing that you will see is the electric, because it's traveling at speed of light, flowing to ground, and then acoustic will come and will come later at different time depending on the location. So your buffer, the majority of your buffer or your majority of your acquisition time should be after your trigger even. So you see the acquisition, the buffer length over here is 2.7 millisecond, but the pre-trigger is only microsecond. So it means little amount of time. So 341 microsecond will be before your trigger, and the majority, so the majority of your buffer will be after in order to see the acoustic coming. This is quite easy. But let's make it reverse. If you are triggering, if your triggering channel over here, I'm highlighted it. If your trigger channel is the acoustic, you want your buffer to be, let's say, same size, 2.7 millisecond, but the trigger will be placed in the middle. What you want is you want to see the electric before, and you may want to see acoustic after. So your buffer will be, let's say, that size, 2 millisecond, but you want your trigger to be placed in the center because you want to see electric on one side and acoustic on the other side. So you can do it manually, or you can ask the system to set it for you. So if you want to do waveform triggered on PD, the even count, we made two options for you, 64 or 1024. This is the averaging. So if you set it to trigger on PD, the buffer will be set like this. So a little bit amount of time before your trigger, and the remaining is after, because everything will be after. But if you want to trig on acoustic event, the trigger must be set in the center. So we will automatically adjust the buffer pre-trigger, that size, and the buffer length, the remaining after. So we will do it for you. So this is why we have preset. We have pre-configure preset for you in order to, let's say, to make sure that you don't miss with the trigger position, buffer length, and pre-trigger. So this is quite important. So what do I recommend is you use the preset. And you see the two other presets are for PRPD. So either quick, or this is low resolution, or high resolution. So it's just a way to remember how to manage your buffer. Now, we take just one step behind. We have identified suspicious PRPDs on the location that we are. Let's say location 1, we have what you're seeing right now. We have repetitive PRPDs on channel acoustic 1, 2, 3, and 4, and also on the electric. This is what you can see here. This is a real example. The same example as the one that have multiple ground strap. A real case. Which channel are we gonna set the triggers on? That's a good question, and there is no bad answer. You see on the right, on the electric, to me, it was suspicious, 3 bumpy things, and on the left, on the acoustic, they look similar, but there is 2 events per cycle, so they are also suspicious. So I did it myself, and I choose the wrong event. No, I didn't choose the wrong. I choose something, and I had to work to prove myself that I was wrong. But there is no good or bad answer. But this is a good training example. So I said to myself, I'm facing a suspicious PRPD. Let's focus on specific events. So I choose wrongly, but I didn't know at the beginning. So I choose wrongly the electric channel because I thought that it was nice, but in fact it was not. So thing is, electric can capture all the surrounding in the substation, all the surrounding electromagnetic emission that can also come from a defective lightning arrestor or defective bushing and other accessories. So the arcing produced by something else will generate electromagnetic emission, and your transformer will act like an antenna and receive this energy, and it will flow to ground, and you will measure it. And this is what happened. So I set the trigger on the first bumpy things, suspicious event over here, and I obtained this signature. Nothing. Okay, it was the waveform was totally noisy. Okay, so I said, okay, I moved it to the little ray, if I could say, the little line, and same thing. So I set the trigger very narrow to around the lines and get nothing, no acoustic out of it. Did the same thing with this little bumpy shape and then this one. So the conclusion was the acoustic that I was looking at was not related to those four electrics events. And this is what I'm looking for. I'm looking to make a relation between the electric and the acoustic. And over there, I was not able to obtain it. So I left the unit at the same place, but now I trigged on channel 4. I isolated just the highest part of the channel 4 activities. And between you and me, channel 1, 2, 3 would also been good. I choose channel 4 because to me it looks a little bit more repetitive because the color is a little bit higher, but all other channel would have been good. But I trigger on channel 4 and this is what I get. So I obtain acoustic. So this is channel 1, 2, 3, 4, and we can see the electric that is appearing out of the noise. So what I want to tell you, you should focus on what you have. You must continue to think that you're looking for relation of acoustic and electric, and you must search for it. So it's not a unit that just press go and let it go. You need to sit down, you need to think what is your next move and take your measurement the best you can, because when you're going to leave the substation, it's done. You cannot come back and you need to come back with answer. So I try, in this example, I try all suspicious event on the HFCT, and then I came back, I said, I'll try acoustic. So now the waveform have been denoised over here. I don't have a location right now. Okay, I set the trigger, I obtain denoise waveform, so I have denoise waveform, and now I need to identify the time of arrival and create vectors and points. Okay, on the left, it's denoise waveforms. What you can do, because you're far way out, what you need to do is to zoom in. So you have a tool that helps you to make a zoom window or zoom out, or this is different type of zoom, but the only one that I really like is this one, the zoom window. So it enables you to zoom just an area, because you don't care about this part here and you don't care about this part. What you want to identify is the time of arrival, those points. So you need to zoom in. That's quite easy. First tool that you should try is to use the auto TOA, so automatic time of arrival. This is a button in the calculator tab, this one here. Okay, just beside the waveform. If you hit the auto TOA, the software will position the time of arrival of each channel. So it's over here. It will do his best, and it does a quite good job, but it's not always the case. But it will position a cursor, a time base on the time of arrival automatically. If the noise is removed, if noise is still present, the software won't be able to tell you or to position the time of arrival. automatic time of arrival works well only if the waveform is denoised. And sometimes to our eyes looks like denoise, it's look clear, but for an algorithm written or coded by human, it's sometimes different. So a way to know that, well, let's say, to have a good indication if the algorithm will work well is to look into measurement, the measurement tab. It could be either before or after, but it gives a good idea. So as you can see, in the measurement tab, you have a little window that tells you if the signals are qualified. Qualified signal means that the system recognizes a time of arrival that can be identified if you press the auto TOA. It does not mean that if they are not qualified that you cannot obtain a position or you cannot work with the signal. It means the algorithm know what to do with it, but your eyes can sometimes be better than that. But this gives a good feeling or a good way, a good indication if your signal are well denoised. So the signal qualification means if the system recognize that they are denoised enough. If you did a good job, the noise was removed, the unit can tell you two things. Okay, the position of or the location of the PD in the tank from the origin or from the AE-150 sensor center. So it depends from the origin or from my actual position. So it's two different things, but it's pointing on the same location. This position is only the first one. It doesn't mean that you don't have others, but if you have position over there, it's a good sign. It's first a good sign. You can also, after the auto TOA, the auto TOA is a good starting point, but you can manually move or adjust the time of arrival. And this is what I really recommend. You start with auto TOA, so all the cursor gets in your windows, and then you use this little button to slide the time of arrival. Because some noise may be present, the software is doing a good job, but sometimes it's slightly moving left or right will change everything. See, this is the same example, a real case that I made myself. The same case with multiple ground. The top is auto TOA only button. So the cursor was located. I had obtained three separate points. You see the points over here, the three possible location, and when I click pinpoints, it gave me 3 points. But when I manual adjustment just a bit, not that much, just slightly move, I was able to obtain 4 points, all grouped in the same location. So it makes not a huge difference because anyway, I was able to obtain accuracy of, let's say, 10 centimeters in a transformer that was 10 meters. So it's like 1%, but it's good to do the best you can with the tool you have. So this is a real case where the auto TOA was good. It gave me, let's say, 90% of the job, but the 10% remaining rely on me, on my eyes, on my judgment to adjust just a little bit the time of arrival. Now, Pinpoints. Pinpoints are easy to understand. They are direct location. They are location of the possible location of PD. But the maximum possible points that we can get is 4. Let me explain. So the first point is obtained with 3 denoise channel. Okay, let me come to first thing. If you get 1 denoise channel, you can have an idea of how far it is. That will be into a spheric possibility. So it's 3-dimension possibility, but located somewhere. But if you get 2 sensor that gets hit by acoustic, you have a direction, but you don't know where it is. You have a direction. But if you got 3 denoise channel hit by acoustic with denoise acoustic, you can get 1 point, 1 3-dimensional points. So 1 point will be obtained with channel 1, 2, and 3. Another point can be obtained with 1, 2, and 4. Another point with 1, 3, and 4, and 2, 3, and 4. So the maximum points that you can get is 4 if all 4 channel are denoise and the time of arrival have been identified. So this is pinpoints. Vector now. Vector quantity is based on the same thing. Okay, vectors are obtained with the same thing. Denoise waveform with time of arrival clearly identified. But the vectors are obtained from a position to tell you a direction of the source. So from position number 1, let's change the slide. From position number 1, you can obtain vector maximum of 4 that tells you that the source is that way. That's the only thing. So with one location, one position, you cannot deduct a PD position. But if you move on position number 2, you can now have another direction. And when you combine both, position 1 and 2, you will obtain a crossing, which is your location. But you will do both. You will do pinpoints and you will do vectors. And those two algorithms will provide you 2 location, okay, 2 XYZ coordinate that are pointing to a similar place, the same area, but they will have 2 different error. They will be distinct because it's 2 algorithm, but you'll do both. But both will be pointing on the same point. So over here you see the pinpoints mathematical average position of the 16 points I made was 420, 148, and 35 centimeters from the origin. And I had 11, not 11 vector, I had 11 vector intersection that cross themselves. And it's not the same color. You see the color over here? This is the color, defined color, the pinpoints and the crossing vector points. It's similar, but not identical. So I get two sets of coordinate. They are within the same range. So as you can see, it's let's say 10 to 15 centimeters away from each other. So it's like, even if it would have been like a ball, that would be more than enough to identify the problems within your transformer. We're not looking to centimeters or millimeters of accuracy. We're looking to an area. We're looking to a location where we can concentrate the search of an arcing, carbon marks, or whatever sign inside the transformer without losing time, without searching everywhere. We're looking to clues and we're looking for an area. So in this example, well, it's an example, but again, it's a real case. You see the standard distance can be defined as an error. So it's the distribution of the point. So 80% of the point were located within 2.9 centimeters from each other. But I don't really care if it's 2.4 or 2.9 or 24 centimeters. That's what I'm looking for. I'm not looking to anything else. This is some tool. Again, we were talking about the calculator tab, but on the display tab over here, we can select the waveform that we want to look at. And this is good to identify the time of arrival. Again, that's all. This is what we're looking for. So time of arrival can be easily identified if we clear or make it disappear the waveform that we're not looking at. So it's like zooming in. So we can show or hide other waveforms to be able to identify the time of arrival. We can also look to an energy or the envelope point of view. And this is what the software, this is what the algorithm is looking at. So energy or the envelope. So you can look it to the envelope or look to the physical waveforms. So it's one or the other. Okay, nothing else. Okay, so we made one trail. We set, let me summarize. We set the PRPD. It was suspect, so we said, yes, it is suspect. We set the trigger, we obtain a waveform, remove the noise, we identify the time of arrival, and we have obtained points and vectors. So the question is now, can I go home? Do I have enough? But if we only have one position, the answer is no. Okay. Ideally, we would cover all the transformer, all site, depending on the site, on the size of the transformer, we will cover all side, front, back, left and right, probably more than one position around it. This could be used to confirm or to obtain vector crossing, or let's say if we made PRPD and the PRPD was not suspect, we will move to another position. So we will move to another position. So let's say that the transformer is totally new, no PDs inside. We are going to first site, we make PRPD, there's nothing suspect, we move to another position, we enter the other position of AE, we take another PRPD, nothing, then we move on the right, on the back, on the left, and we take PRPDs all over, and the result will be, I'm done. There is no suspicious activity in this transformer. But something to remember, if there's nothing, it doesn't mean that the transformer does not have PDs inside. It means that today, at the inspection time, nothing was suspicious. It doesn't mean that tonight or this weekend, when the activity will be different. Let's say the load will be less, the voltage will be higher, the humidity will get in. We may get PDs at this time, but right now, at inspection time, I am looking to nothing. There is no suspicious. But if you do have suspicious and you make points and you make vector, you should continue around your transformer to cover all phases to have a complete view of your transformer. So the next section now, let's come back to this training. Next section is the next position. Where should we move? And there are clues that you should use to change to your next position. So the next position, let's look to those two examples. We have clear the noise waveform, and the first waveform to be I'm starting the first sensor to capture acoustic pressure waves is sensor number 3. So this one is number 3. So it means that the source is located bottom left. So you won't move right. The goal is to move as close as possible to the source. So your next move, based on the information obtained, your next position will be somewhere bottom left. This one is different. This is sensor number 1. Sensor number 1 is capturing acoustic first. So the source is located top right. Don't move bottom left. The goal is to get as close as possible where the energy is higher. So this is what we are looking for. Okay, moving as close as possible to the source. So this is the direction. But now, the distance. How far should I move? And again, we have not a tool, but we have, well, let's say, yeah, tool that will help us to identify or to give you an idea of how far should I move. So we have identified, in this example, we see that channel 2 and channel 3 are capturing acoustic, let's say about in the same time. So my direction is left. Okay. Channel 2 and 3 are, it means that I'm moving not bottom or top left, I'm moving left. How far? So you can obtain this information by the electric, the difference between the electric channel over here and the time of variable of the acoustic. So you see over here on acoustic channel 3, so the cursor time, okay, from PD, okay, from the electric starting point, if I could call it like this, it's 493 microsecond. So 493 microsecond, if it's only traveling, the acoustic is only traveling in oil, it means it's 69 centimeters away. And if it would be only traveling in steel, it's 2.5 meters. But we don't know if we are direct path or combined path. So the thing that we know, the source could be between 2 meters and 69 centimeters. So it's in between. So it gives you a range, because in this example, you see the transformer is 6 meters. It's around 5.7 meters. So don't move more than 3 meters. So roughly move in between. So 1 meters, it depends on the mechanical structure, but it gives you an idea of how far you should. Okay, but if the information tells you you should move left, and then you move left, and it says you should move right, you have the information that it's in between. Now, you must keep your brain alive to identify clue and where should you move, how far should I move, am I having suspicious thing, should I make other measurement, should I take measurement on another ground, and all those things. You must keep your brain alive to make a good inspection. Lastly, I think it's my last slide, uh, generating a report. You may have noticed that there is no save button. So everything that you're doing, every action that you are making will be saved based on time. So it takes the computer times and save everything as timestamp. So you close it, everything's okay. One thing, close it if you're working with laptop, which makes sense. Before closing your the lip of your laptop, the cover, close Miradar. Okay, sometimes if you ran out of batteries, Miradar doesn't have time to close the session, and then you get in problem. So close Miradar before shutting down your computer or make it hibernate. So everything is timestamped, and we are using Microsoft Words to export everything we did. So everything you did can be exported in Words, and then you can edit, add your comment, add your logo or whatever you need. You can export everything into Microsoft Word to generate a report on your own. So we're not exporting to PDF, which is it's hard to edit a PDF file. So this is why we're using Microsoft Words. Okay, I'm done now. This was a training. We have tools on the web, so we have a refresh training, a video on YouTube that you could watch. We also have the manual, which also is a good way of learning. I remain available. You can contact me anytime if you have any question. And I hope this training will help you in your AE-150 inspection. So thanks for watching.